Hi guys, welcome back to my channel Pirai Academy. In the series of data structure playlist, today we are going to implement AVL tree. And before implementing the AVL tree, I will be giving you some basic foundation so that it will be helpful when implementing the AVL tree. Okay, so the prerequisite of AVL tree is recursion, stack, and binary search tree implementation. And these three videos will be given in the description. Just go and watch it, then continue this video so that you can understand this clearly. Okay, so AVL tree is also called as balanced binary search tree. So binary search tree plus balancing factor or balanced tree will be the AVL tree. Okay, now you can understand this clearly. So see here, ADTs, what are all the ADTs we are going to implement in AVL tree are insertion, deletion, get minimum, maximum, and traversing. Okay, so these are all implemented in binary search tree also. Now it is going to be implemented in a balanced manner. Okay, so as I already told in the types of tree itself, okay, like binary search tree has some disadvantage. Like if the binary search tree is like a skew tree, then here the time complexity for insertion or deletion or searching. So here just add searching also. So searching is not big deal. Okay, searching. So if I am doing a searching operation in a skew tree of whether it is of a binary search tree, then the time complexity will be of O of n. Okay, but in balanced binary search tree or in AVL tree, the time complexity will be of O of log n by using the balancing factor. Okay, so it will be self-balancing binary search tree. Fine. So let's get started. So see here, the basic understanding of the AVL tree is this is a binary search tree. See here, for all node, its left subtree is always less than its value. Meanwhile, its right subtree will be always greater than its value. For 50, see here, all the left subtree are less than and all the right subtree are greater. For all nodes, this property will be followed. So I can definitely tell this it is a binary search tree. Okay, now there is also a thing you want to know, balancing factor. So what is mean by balancing factor? So see here, for this 25, if I want to find some balancing factor for some node, then the formula will be height of left subtree minus height of right subtree will be my balancing factor. Okay, for this 25, what is the left subtree height? 0. Right subtree height is also 0. So 0 minus 0 will be 0. For 20, left subtree will be 0. Right subtree is 1. So 0 minus 1, it will be minus 1. For 30, its left subtree height is 2. Okay, and right subtree value is 0. So 2 minus 0 will be 2. For 50, its left subtree value is 3 nodes, right? So 3, and then in right subtree it will be only 2, either this path or this path. In either one of the path it will be only 2 only. Okay, the maximum height. Okay, so that's the reason why I'm getting here as 3 minus 2 which is equal to 1. Similarly for these nodes also. Fine. So this is how we will be finding the balancing factor, and this balancing factor should be in a range of -1 to 1, which means the number should be equal to either -1 or 0 or 1. If it is not equal to these numbers, then it is not a balanced tree. So see here it is what? 2. So here itself I can tell you that it is a binary search tree, but it is not a AVL tree. Can you understand this? So that's the reason why I am telling you that it is self-balancing binary search tree. Okay, so before entering into the implementation of the AVL tree, first let us complete the 4 rules, or you want to know about these 4 things so that it will be much more useful when it comes to the balancing. Okay, because AVL tree is a self-balancing binary search tree, right? We already know about how to implement the binary search tree. Now we want to focus on this self-balancing. So that's the reason why I am telling this. Okay, so the first one is left rotation. Okay, so to understand this, see this tree, see this example tree here. What is the balancing factor of this 12? It is 0. Balancing factor of 20, 0. What is the balancing factor of 15? It is also 0. Yes. What is the balancing factor of 10? It is 0 minus 2, which is equal to minus 2, which is equal to minus 2. So from here, I can tell you that it is not a balanced tree. Yes, at which node? At the node number called 10. So at this particular point, it is not balanced. So what I'm going to do is, see this carefully, listen this carefully. What I'm going to do is, I will be dragging it towards the left side. I will be dragging this towards the left side, which means this side. If I drag it towards the left side, then 15 goes to the top. 15 goes to the top, okay? And then my 20 goes to the 15's right side. Meanwhile, this 10 will be my 15's left child. Just imagine like pulling like this, pulling from 10 to like this, so that 10 will be coming down, 15 will be going up, okay? Meanwhile, 15's left child will be 10, 15's right side will be remaining 20 alone. Now, you have a doubt where I want to insert this 12. Okay, logically in binary search tree, where you will be inserting the 12? See here, 12 is less than 15 and greater than 10. So, it will be obviously to the right side of the 10. Yes. Now, just see what is the what is the balancing factor of each and every node. So, see here, for this node, it is 0. For this, it will be minus 1. For this, it will be 0. For this, it will be 2 minus 1, which is equal to 2. Okay, so 2 minus 1, which is equal to 1. Okay, so all the node are balanced. Now I can tell you that it is a balanced tree. Okay, now let us see the code for this particular thing. So this is a code snippet. So after this, we can go to the next thing. So see here, x. So here, this is that 10. Let me redraw that so that it will be more clear. So 10, 15, 20, 12. Okay, now listen this carefully. So this is the particular node that is not balanced, right? So this is going to be the x. Okay, now y going to be x right. Okay, now t going to be y's left, t2. Now how I am going to rotate is these two lines. Y's left is going to be x, which means y is 15, right? 15's left is going to be what? Going to be x. So which means here comes 10. Okay, now x right is going to be what? T2, which means here it will be 12, the T2. Okay, now the 15's right child in default itself 20. So this is how my tree looks like. Can you understand this? So this is the code implementation or code snippet for left rotation. Now let us get into the right rotation. For right rotation, see this example. Here, what is the balancing factor? 0, 0, 0. But here it will be what? 2. 2 is not a valid balancing factor, right? So here we want to do a right rotation, because when I am doing a right rotation like this, when I am pulling it towards the right side, it will be balanced. Can you understand this? Later on, we will be seeing the conditions for this. Now, just understand, pulling towards the right side will be balancing it. Okay, if I am pulling this towards the right side, then 20 will be the right child of 15. 15 goes to the top, and 15's right child going to be the 20. Yes. Now, 15's left child is obviously 10. Obviously 10, because 10 is the default itself. Okay. Now, our only worries is about 18. Okay. In BST, where the 18 will be inserted, 18 is greater than 15. Meanwhile, it is less than 20. So obviously the left child of 20. Okay, let me redraw this and just dry run with the purpose of with the use of this code snippet. Yes. Now this is going to be y. Okay, it is just a variable. Okay, it is not like we only place this as y or x. That's the reason why I'm just taking any of these variables. Okay, now it is y. Now x is equal to what? Y is left. So this is going to be x. Now t2 is x right. So this is going to be t2. Okay, now how I am going to rotate this? First of all, x right. So which means 15's right side is going to be y, which means 20. Okay, now y is left going to be t2, which means here comes 18. So defaultly 15's left child is what? 10. So 10 will be remain there itself. So this is going to be the tree after balancing it, after right rotation. Fine. Now, there are two more cases, which is left to right rotation, right to left rotation. From the name itself, you can understand we are going to rotate in left side first and right side next, or right side first and left side next. So see here. So here, balancing factor will be 0 for 20, and for 10 it will be -1, and for 30 it will be 2. 2 is not a valid balancing factor, right? So now what we are going to do is we are going to we are going to rotate in a left side first, then we are going to rotate in a right side. See here, if I just rotate here like this in a left side rotation, then my tree something looks like 30, 20, then 10. Can you understand this? Yes, this is the first step. In next step, I am going to rotate in a right side like this. Okay, if I pull it in a right side, then it will be 20, 30, 10. This is balanced, right? So this is what the output also. Now hope you understand this. So the name itself telling me like, hey, pull it left first, so that it will be aligned like a skew tree. Now pull it right, so that it will be balanced. Can you understand the algorithm, right? So it is a combination of the left and the right. I'll be showing this in a code itself. Okay, it is not a big deal. Okay, now see here, right, left. Meanwhile here also it is 0. Here it will be 1, and here it will be -2 for the balancing factor, right? Now here I want to do a right rotation here first, then do a left rotation entirely. That's the reason why the name itself what? Right left rotation. So if I do a right rotation, then it will be like 10, 20. Sorry. So it will be like 15, 20, right? 15 and 20. Now I am doing a left rotation. If I do a left rotation, it will be like 15, 10, here comes 20. That's it. So this is the balanced tree. Fine. So that's it. Now let's get started with the implementation. For the implementation, as I already told you, first we will be completing the insertion, then deletion, then searching, and traversing will be as much as easy. Okay. So let me finish the insertion first, so that you have a clear understanding on the AVL tree. Now I just imagine like you already I assume like you already saw my binary search tree and binary tree implementation. There I have used much more in-depth concepts. Like I will be explaining in a depth, but here I will be explaining in a above layer only. Okay, but the AVL tree, the balancing factor will be explained in a well manner in this video, but the overall the binary search tree, the repetition part will be not explained like that video. Okay, so because the video will be in a lengthy, that's the reason I am going like this. Okay, fine. So here a node alone have 4 attributes: left, right, root value, and then height. Height is added. That's it. Okay, all other 3 will be similar to the binary tree and binary search tree. Height alone added. Why? We need to find whether it is a balanced or not. For balancing factor, we need left subtree height and right subtree height, which will be stored in the node itself. Can you understand this? Okay, so this is how a node will be. Okay, fine. So let me just construct this so that you can understand this clearly. First, it is 30. So if I insert 30, initially there is nothing, so insert 30 as it is. So see here, in binary tree and binary search tree, I have done like this. Like I am giving the entire node as a drawing. Okay, now I just put a circle and assume like it has height, it has left child and right child also. Okay, so come up with me so that you can understand this clearly. Okay, now 20. Okay, 20 is less than 30 or greater than 30. It is less than 30. Whether 30 has left child? No. Then add 20 here. This is what we will be doing in a binary search tree also. Yes. Now check for the balancing factor for 20 and the 30. What is the balancing factor for 20? It is 0. What is the balancing factor for 30? It is 1. So both are valid. So leave as it is. Now 10. 10 means 10 is lesser than 30, lesser than 20. 20 doesn't have left child, so add 10 here. Now comes the twist. Here 0, here 1, here 2. 2, which means what? Which means it is not a balanced thing. Let me put the numbers. Okay, not a balance. So what we are going to do now, see here, let me give you a tip. So see here, first thing, here we are going to do a RR rotation, or right rotation, okay, which means I will be pulling like this, so that my resultant will be like 20, and 20's right side will be 30 and its left side going to be 10, which means something like here comes 20, here comes 10, and here comes 30. Yes, now what is the condition that leads to this answer, that leads to the right rotation? See here, the first thing, it is overloaded in the left side. Why I am telling it is overloaded in the left side? Because it is what? It is 2. 2 means left subtree height is greater. So from here itself, I can tell you that if the balancing factor value, sorry, I will be writing like this. Okay, if the balancing factor value is greater than 1, and also, what is the next thing? The newly inserted value, that key, this 10 is lesser than this particular node's left child. See here, this particular node is a non-balanced thing, right? So its left child, this 20, whether for example, if it is 25, then it will be like this. Forgot about 10. If it is 25, then it will be like this. At that particular point, it will be like what? It will be like LR rotation, because it is like this. Now it is not like this. Instead, it is like this plane line. That's the reason why we are going to do a right rotation to check whether newly inserted node is particularly in this angle, or in this left tree or in the right tree. We are going to do what? We are going to check whether key is less than that root, this particular node, this root left value. That's it. Can I understand this condition? Yes. So this is the condition for the right rotation. Okay. Now what is the next thing? We want to add 25. Okay, add 25. 25 is greater than 20. Meanwhile, it is less than 30. So add 25 here. Now check whether all are balanced. Yes, all are balanced. You may check by yourself. Now 28 is greater than 20, which is less than 30, but it is greater than 25. So you will be adding something like here. Now check whether the height is balanced or not. Okay, so see here, it is 0. Now here it is what? 0 minus 1, which is equal to minus 1. So it is also balanced. So come to this 30. For this 30, what is the balancing factor? It is going to be 2 minus 0, which is equal to 2. Meanwhile, all other which is equal to 2, right? So first we want to balance this, then we want to check the all other. Yes. So how we are going to balance it? So see here, this is the condition I talked in previous itself. Here I put the 25, right? In that particular time, I will be having like this condition. So at this particular condition, what we are going to do? We are going to do LR rotation. So I am going to do LR rotation. Okay. When I am going to do a LR rotation, see, tell me the condition. So balancing factor is greater than 1, and also my key is greater than root left child's value. Can you understand this? This 30's left child is 25. Its value is lesser than the newly inserted element's value. In that particular scenario, this will be occurring. What? Right rotation. So by doing this, we will be getting a balanced tree. Okay. Now let's do the left right rotation. So after doing the left right rotation, it will be like 20, 10, and here this will be rotated like this, so that here comes the 28 and here comes the 25. Can I understand this? So here comes 28 and here comes 25. So 28 goes up and here comes 30 and here comes 25. I know like it will be not understandable at first, but if you cannot understand this, just go again once again, okay, from first, so that you can understand this clearly. Okay, so I am trying my best to make you understand this. Okay, fine. So now whether all are balanced? Yes, all are balanced. Okay, you may check. Fine. Now it is 40. So 40 is greater than 20 and greater than 28 and greater than 30 also. So here comes 40. Here comes 40. Now check whether everything is balanced. So 40 is 0. Balancing factor of 40 is 0. Now balancing factor of 30 is 1. Sorry, 0 minus 1, which is equal to minus 1. Here also 0. So here comes 1 minus 2, which is equal to minus 1, and here it is 0. Now for 20 it is 1 minus 1, 2, 3. So 3, which is equal to minus 2, minus 2. So at this particular point, what we got? We got minus 2. So what we are going to do now? So here comes what? Minus 2. So minus 2 is, I'm insisting what? It is not balanced. So at this particular point, what I'm going to do? I'm going to rotate in left side. After rotating into a left side, what will be my tree looks like? So let me first write the tree, then we can write the conditions. Okay, so if I just rotate in the left side, then it will be something like, so here comes 28, here comes 20, and 20's left child is 10, and 28's right child is 30, and here comes 40, and what is the remaining thing? It is 25, right? 25 will be inserted here. Yes, now hope you understand this. So here we did what? We did left rotation. So left rotation here. This rotation is done in this step. Okay. Now what is the condition that occurred here? First of all, the balancing factor is less than minus 1. It is the first condition, and the newly inserted key, this 40 is greater than my root right's value, which is greater than the 28. That's the reason why we are just getting like this structure. If the key's value is less than the root's right, then we will be getting like this, which means we want to do what? We want to do oral rotation. Can you understand this? So now if you check the balancing factor, it will be smooth. Okay. Now the next thing is we want to insert 50. Okay, insert 50. 50 is greater than 28, 50 is greater than 30, 50 is greater than 40, and 40 doesn't have any right child. So just insert here as 50. Now hope you understand this. Okay. Now what is the balancing factor here? It is 0. Here it is 0 minus 1, which is equal to minus 1. Here it is 0 minus 2, which is equal to minus 2. So at this particular point, it is not balanced. So what we are going to do now? We are again we are going to do what? We are going to do left rotation. So left rotation. So here we can again use this condition also. See here, whether the balancing factor is minus 1, less than minus 1. Yes, it is minus 2, which is obviously less than minus 1. And newly inserted key is greater than root's right value. So 50 is greater than 40. Yes, obviously. Then what you are waiting for? Just do a left rotation. If I am doing a left rotation, my tree something looks like 28, 20. So here all unchanged. Okay. So here comes 10, and here comes 25, and here comes 30. Sorry. So here comes 40, and here comes 30, and here comes 50. Now it is obviously balanced. Yes. Now what is the next thing? Next thing is 55. We are going to insert 55. If I am going to insert 55, whether 55 is greater than 28, yes, greater than 40, greater than 50, and it will be inserted here. Now check for the balancing factor. So here 0. Here it will be what? It will be 0 minus 1, which is equal to minus 1. Here it will be 0. Here 1 minus 2, which is equal to minus 1. Here all are balanced, right? You can also cross check it. Okay, so everything is balanced, so leave as it is. Let me cancel it out. Okay, now what is the next thing? Next thing is 52. So 52 will be inserted something like here, right? Because 52 is greater than 28, 40 and 50, but it is less than 52, so it is inserted here. Now check for the balancing factor. So it is 0, here comes 1, and here comes what? 0 minus 2, which is equal to minus 2. So it is not balanced. So first balancing it. So here what we are going to do, we are first doing a right rotation, then we are going to do a left rotation. So it will be RL rotation. RL rotation, where here we are going to do this kind of rotation. So let me do here. So after doing this, how my tree looks like? 28, 20, 10, 25, and here comes 40. Oh, just a minute. And here comes 40, and then here comes 30. Then here comes, if I do a left rotation, 52 comes up, right? So 52, here comes 50, and here comes 55. Can I understand this? Yes. So this is how it will be changed when we are doing a RL rotation. So after doing this RL rotation, we noted that the tree is completely changed like this. Now check for the all the balancing factor. So here 0, 0, here also 0, and here 0. The balancing factor here is 1 minus 2, which is equal to minus 1, and here it will be like 2 minus 3, right? 2 minus 3 is equal to minus 1, and here 0, here 0, 0. So all are balanced. So that's it. That's it. Now the important thing, what is the condition? So condition will be balancing factor. So here it came less minus 2, right? So balancing factor should be less than minus 1, and also my key should be what? Less than root right value. So when these two conditions are satisfied, then I am going to do a right left rotation. Okay, you can see here. So if I get like roots right value is greater than the key only, we will be getting like this structure. That's the reason why I am just writing this condition. Now hope you understand why we are writing these particular conditions. Okay, because many are memorizing this. I have seen my friends in college also, they will be memorizing these steps. That's the reason why I am just coming up with how these conditions are taken out. Okay, fine. So this is how the insertion will be taking part, and these insertions will be also used in gate examination also. In gate examination, they will be giving some set of elements, and they will be asking you to construct the AVL tree, and they will be asking you to just fill the missing parts like that, or they will be just telling you to just like this particular node, the last node, what will be the last node, or what will be the last node's parent, like that. So anyhow, this construction of AVL tree will be much more helpful. Okay, and next thing that is more helpful is deletion. They'll be deleting some node, and they'll be asking what is the parent of last node, or what will be the grandparent of last node, like that. In end semester also, for me they asked in the end semester also. So let us see the deletion. Let me clear this off, then we can see the deletion. So now we are going to see about the deletion. Okay, now in AVL tree, the deletion taking place like a binary search tree. Okay, so for example, if I am going to delete 55, then I will be just searching here whether 55 is greater than 28, yes. Whether 55 is greater than 40, yes. Whether 55 is greater than 52, yes. Whether 55 is greater than 55 or equal to 55 or less than 55, it is equal to 55, right? So I found out the 55 back here, this particular place. Okay, whether it has 0 child or 1 child or 2 child, because these are the number of child each node have, right? So I am going to check whether it has how many number of child. So it has 0 number of child, because it doesn't have any left child and right child, right? So in this scenario, you can easily delete this. Just delete it. Delete that particular node. That's it. That's it. And make its parent to null. Okay, it's parent to null, or you can just delete it. That's it. Okay, fine. Now, like when I'm deleting it, when I'm returning this value, it will be returning null or null. Okay, when I'm showing in the code, I'll be showing this clearly. It will be more of backtracking concept. Okay, now for example, if I'm going to delete 52, if I'm going to delete 52, okay, now I'll be checking here whether 52 is greater than 28. Yes, then go here. Whether 52 is greater than 40. Yes, then go here. Whether 52, here comes 52, so 52 is equal to 52, right? So I'm going to delete it. Now check whether it has 0, 1 or 2 child. It has one child. It has one child. So don't do anything. Just make its value, or make this node to be deleted, and just connect this value to this. Like what I'm going to tell means, just delete the value, that particular value, this particular value. Let me just a minute. Just delete this particular value. Okay, and just update there as node as, what is the node I just erased? 50, right? So 50. That's it. Can you understand this? Just delete the 52. Just delete the 52 and just connect or return its left child value to the parent, so that there will be a linkage like this between them. Can you understand this? Okay, so I understand, like it will be a bit complicated, but while we are seeing in a code, it will be more clear. Okay, and if you already saw the binary search tree, you can easily understand this. Okay, fine. Now we want to delete 28. Let make this as a really interesting. Okay, now I want to delete 28. Okay, here is 28. Now I'm going to delete it. So if I want to delete this 28, what should I do? I want to check whether it has 0, 1 or 2 child. It has 2 child. Whenever it is 2 children, it will be a big headache. Okay, now let's make it simple. So see here, always remember this. If I want to delete some node that have 2 children, then you can either go to the left subtree and take the maximum value, or go to the right subtree and take the minimum value. Why I'm taking a maximum value in the left subtree? Because the maximum value in the left subtree is going to be the immediate previous value of the root. See here, 28. What is the maximum value in the left subtree? It is 25. Immediate previous number, right? Why I'm telling you to take the minimum value in the right subtree? Because here it is 30, here 28. 30 is the immediate next value of 28 in this tree, right? So that's the reason why take either this or this. Now I am going to tell you to take in a right subtree minimum value. So what is the right subtree minimum value? It is 30. It is 30, right? So make this as 30. This as 30 and go and delete 30. Now go and delete 30 means again do a recursion call for 30 for the deletion process. Now whether 30 has 0, 1 or 2 child, it has 0 child. So don't worry, just delete it. Now check for the balancing factor, whether all are balanced. Yes, all are balanced. So leave it. So here you are worrying about, go and see all the nodes as whether it is balanced or not, right? In real time, when we are backtracking in a recursion, that we can check for the balancing. That I will be showing in the code. Okay, don't worry. As of now, if you understand some logics, that's more than enough. Okay, when we are going for a code implementation, there you can really understand what we are going to do. Fine. Now this is my final tree after deleting this. Okay, if I want to delete like 30, no 30 not. If I want to delete 100, okay, then I'll be going here. Whether 100 is greater than 30, yes, go here. Whether 100 is greater than 40, yes, go here. Whether 100 is greater than 50, yes, go to its right side. Right side is null. So from here I can tell you that 100 is not present. 100 is not present. Yes, okay, we finished almost everything. Now for finding the minimum and the maximum and searching, for finding the minimum, maximum and searching, these three operations will be taking taking the same algorithm as the binary search tree. So I am not going to repeat these three processes, as you already saw my binary search tree playlist, sorry, video. Okay, now let's discuss about the time complexity that is required. So what is the time complexity for all operations? So first operation is insertion, right? For insertion, what is the time complexity? It will be O of log n, because it is a balanced tree and we only go to the height. So in AVL tree, it has a property like height will be approximately equal to log n. Okay, so this will be more important when we are going for a competitive programming or for GATE examination also. Okay, so that's the reason it is O of log n or O of height. Okay, now come for a deletion. Deletion also it will be O of log n. Okay, come for minimum and maximum. There also it will be O of log n. Okay, come for searching. There also it will be O of log n. So all the operations can be done in O of log n except the traversing. As you know, traversing means you want to visit all the nodes. All the nodes. There you will be taking O of n. So it also have a property like when you are traversing in a in-order traversal. When you are traversing in in-order traversal, it will be in a sorted order, because it is also a binary search tree type only. Okay, so it is quite different. It is balanced binary search tree. Now, hope you understand how we made the disadvantage of the binary search tree into an advantage type. Okay, if you remember my story which I told in types of trees, you can understand how we are making this efficient further. So this is the code implementation. So here I will be implementing this code using C++. If you want Java or Python code, you can go and search in the description. And this code will be approximately equal to the binary search tree. So here also the binary search tree concept will be implemented. The only difference is we will be checking for the balance factor and balancing each and every time. That's it. Okay, so let's get started. So here I am using a class node to describe what are all the attributes that are holded by the node. Okay, here you can also use structure because it is a C++. Okay, now here I am having four attributes: key, left address, right address, and height of that particular node. For the use of the balancing factor, I'll be showing in the code how it is useful in a balancing factor. Okay, now in constructor I will be getting the key value of the particular node and I'll be initializing it, and left and right will be null pointer. Meanwhile the height will be initially 1. Okay, fine. So this is the class AVL tree. So this class is going to be implementing all the ADTs of the AVL tree. Okay, fine. So see here, first of all, get height. So this is not a ADT that I have mentioned. It is going to be the helper function. Okay, there is difference between ADT and helper function. It also can be made as a ADT, but here I am using this for a helper function. In this helper function, I'll be getting some node, and I'll be returning what is the height of that particular node if exist. Else, if it does not exist, then it will be 0. That's the purpose of implementing this get height function. Okay. Now get balance. So this is the function that gets the node as a parameter, and if that node is equal to null, then it will be returning 0. Else it will be returning what is the balancing factor. So what is the balancing factor? How we are going to find it? Just take the roots left subtree height and get the roots right subtree height and just do a difference between them. That's going to be the balancing factor. Now here comes the right rotation. So in right rotation, as you know, if I want to rotate some particular node in a right rotation, then I will be getting that particular node as a parameter, and I'll be doing these 4 steps. This 4 steps I have already completed in a drawing explanation itself. Right now, the next thing I'm going to do is I want to update the height of 2 nodes, Y node and the X node, right? So I'll be updating this. How? I will be updating like 1 plus maximum among its left subtree and maximum among right subtree. That's it. So why I'm taking here as 1? Because take myself as one of the node and take my left subtree node either, or take my right subtree node either of them, which I will be taking, which is maximum that I will be taking. Okay, same thing will be applied for this x also. You understand this? And finally, I'll be returning x because it is the new root of the particular place. Can you understand this? I'll be getting the y after doing the right rotation. X will be the top. X will be the root. That's the reason why I am returning x. Can you understand this? Yes. Now, same thing is done in the left rotation also. These 4 lines, which I taught in the drawing explanation, and these 2 lines, which is similar to this 2 lines. Okay. And at last, I will be returning y. I will be getting x and returning y. That's it. 2 things are same. Okay. Fine. Now, let's get into the important functionality insert. So, see here. In insert, I'll be getting a root and a key. Okay. Now, if the root doesn't exist, then make that given key as the root. Can you understand this? Okay. Now, if key is less than root key, then what should I do? I'll be going to the left subtree. I'll be going to the left subtree. That's the reason why my left child equal to insert of that key to my left subtree. That's the meaning of this one line. You understand this? Okay. Now, LF, my key is greater than the roots key. Then I want to go to the right subtree and update that particular value in my right child. Again, I am telling you, if you cannot understand the backtracking and recursion concept, you cannot understand this also. Okay. So, please thorough that and then come to this topic. Okay. Because it is a non-linear data structure and it is tougher than implementing the binary tree or linked list. So, please go and watch the recursion and backtracking, then come up with this video. Okay. Now, else I'll be returning the root itself. Okay, because to avoid the duplication. Fine. So this is I didn't told in the drawing explanation, but still in AVL tree or binary search tree there will be no duplication allowed, right? So at that particular point I'll be just returning the root itself. Okay, fine. Then what I am going to do? See here, root height is equal to 1 plus maximum of its left subtree and right subtree height. I have updated this root height successfully. See here, why I am updating this after all these conditions? Because I am writing a recursion code. I am writing a recursion code. Recursion code means it will be once again backtrack. When I am completing these all recursion calls or this all conditions, then my control flow comes to this particular line. At this particular line, when it is backtracking, I will be at that point itself, I will be making this as balanced if it is not balanced. That's the reason why I am taking and updating the root height. First step. The next step is I will be taking the balance factor by getting the by calling the get balance of that particular node. Okay. Now I am going to check whether it is in the one of these 4 conditions. These 4 conditions I already taught you in the drawing explanation, and I have told you how we are going to derive these 4 conditions. So see here, balance factor is greater than 1 and key is less than root left key value. Then what I am going to do? I am going to right rotate the root. Okay, if the balance is less than -1 and key is greater than root right key, then I am going to do left rotation on root. Can you understand this? And I will be returning it. I will be returning it so that it will be just updated in a recursion called statement. Fine. And then come here. This condition is more than important. Okay. So see here, balance is greater than 1 and key is greater than root left key. Then what should I do? I will be doing a LR rotation, left right rotation, right? For doing the LR rotation, first I want to do roots left is equal to left rotation. Can you understand this? Yes. Then I will be returning the right rotation of the root and returning the value. That's it. Can you understand this? Meanwhile, in the right left rotation, the RL rotation, there I will be just taking the right child value and right child and updating this as right rotator value and returning the left rotator of the root. That's it. Can you understand this? That itself I have told you. like see here, if it is like this, then I want to first rotate this 2 in a right, then I'll be rotating this entirely to the left. If it is like this, then I'll be rotating first to the left, then I'll be rotating towards the right. So I already taught this in a drawing explanation. So that's the same thing I have done here also. Okay, at last I'll be retaining a root. Why I'm retaining a root? Because here I want to update in the left child and the right child, right? If nothing happened, then I will be at last returning the root. These all conditions failed, then I will be returning the root. That's it. Okay, fine. Now, as you know, get minimum and get maximum. So these two functionalities will be as same as the binary search tree, but the only difference is the time complexity of doing these two things will be O of log n. Meanwhile, in binary search tree, the time complexity will be O of n. When it is a worst case like skew tree. Okay. Now delete node. In delete node, I'll be getting root and also key to be deleted. Now, if there is root, there is no root, then I'll be returning null. Okay. Here you can also return null pointer, but here I am returning right root. Okay, fine. Now, if the key is less than the root key, then I want to go to the left subtree. So that's the reason why I am taking a left child and I am just calling the left subtree and telling it to delete the key that I have given in the recursion call. Same thing for the right subtree also. If the key is greater than the root key, okay. Else means what? Else means key is equal to the root key. I am standing at the particular root which is equal to the key I have given. If I am at that particular point, what do I do? I want to check whether it has 0 or 1 or 2 child, right? So first of all, I am checking it. So not root left or not root right, which means either it doesn't have left child or it doesn't have right child or it doesn't have both. Then what should I do? I'll be taking node star temp is equal to root left, whether I am checking whether it has root left, which means whether it has left child. If it has left child, then take it. Else take right child and store it in the temp. Okay. Now, while temp is null, which means what? Which means I didn't have either left child, I didn't have right child. Then at that particular scenario, what we are going to do? We are just going to delete that particular root. That's it. So that's the reason why temp is equal to root and root is equal to null pointer. That's it. Can you understand this? Yes. Now, else means we have one child, either it is left or right. That's not matter, right? At that particular point, I'll be assigning the temp value to the root and deleting the temp at last, regardless of these two conditions. At last, I'll be deleting the temp. Okay. Now, else means what? It has two children. So this is going to be the tougher part, right? But here it is same as the binary search tree. So see here, temp is equal to get minimum from the right subtree. I'm getting the minimum from the right subtree, and root key will be that that particular key we have got from the right subtree minimum value, and I'll be updating that to the root key. That's it. Okay. And now root right is equal to just go and delete the particular key that I have taken from the right subtree That's it. So it will be again a recursion call. Can you understand this? Now come here. If not root, return the root. So I have again returned it, right? Okay, sorry. It is like we didn't have that particular node. Like I am giving you to delete 10. Then you didn't have that 10 in your tree. Then you will be just returning there. Okay. And then at last, what I am going to do, I will be just balancing it, right? So for that, I will be taking the root height and updating the root height first. Now I am taking the balance factor. Now I am checking whether it is fallen under these 4 categories. If any of them, then I will be doing left rotation or right rotation or LR rotation or RL rotation, and at last I will be returning the root itself. So these things will be similar to the insertion and deletion, but the only difference is we are first inserting it and doing a balancing. Here we first delete it and doing the balancing. So I can tell you that the only difference is these lines. If you add these lines to your binary search tree, it will be AVL tree. Yes. Now here comes in order, pre-order, post order, and printing it, and you also do a level order traversal. That's your wish. Okay, so I already taught these things, so that's it. So that's the whole thing for the AVL tree. Now in the main function, you may just do like in a manual format, or you can also do a menu driven program. So this is the entire thing about AVL tree. And if you really like this video and subscribe to my channel, and don't skip any videos in this playlist, because all videos will be helpful once you are going for a competitive programming. And importantly, if you have any doubts, comment below, and if you have found out any mistakes in this code, let me know that. Just comment below. Okay, and I know it is hard to understand AVL tree. Okay, when I'm studying at first, I too just struggled in AVL tree. Okay, but when you are practicing that and when you are dry running it and implementing this code by yourself, it will be much more easier than you think. Okay, all you want to know about is recursion and backtracking. So that's the more important thing when you are going for a non-linear data structure, because now you are seeing only the implementation of the AVL tree. In point of view of comparative programming, in comparative programming point of view, this is a easy program. Okay, when you are going for a tougher program, you want to know about the recursion and backtracking in clear manner. Like when I am telling you to do for loop or while loop, you will be doing in a mind itself, right? You want to know this recursion like that looping, similar to looping. You want to process these recursion backtracking in your mind. You want to put that recursion stack and tree in your mind. Okay, you want to think like that. Then only you can just come up with some solution and you can just solve the competitive programming. So I hope it is much more clear, this video, and I hope you understood some of them. I don't want you to understand the entire thing, but you can take some things, right? You can understand some things. That's enough. Okay, so apart from that, if you just watch this video 2 or 3 times, you can definitely understand the AVL implementation. Okay, thank you.